welcome to the Deep Dive. Today, we're stepping into, well, what feels like the future of making things metal 3D printing.
Additive manufacturing, or AM.
Right, AM. We're talking about building really critical components, things for aerospace, high-performance car engines, even medical implants.
And the technology gives engineers incredible freedom, doesn't it? Designing shapes that were basically impossible before.
Totally revolutionary.
Yeah.
But there's a catch, a kind of built-in flaw, right?
That's the core issue. When you print metal layer by tiny layer, you get these cycles of intense heating and cooling, really rapid. And those extreme temperature changes, those thermal gradients, they bake in a problem, residual stresses. And they're the bad kind, tensile stresses.
Tensile, so pulling forces.
Exactly. Forces that can compromise the part's strength, its integrity, maybe even shorten its lifespan before it's ever used.
So that's the conflict we're digging into. We're focusing on a specific material, TC4 titanium alloy. Super important in those industries you mentioned.
It really is a workhorse material.
And the research we've looked at tackles this stress problem head on.
Yeah.
They're using a pretty high-tech fix, laser shock peening, LSP.
Right, LSP. And our goal here isn't just to talk about, measuring stuff in the lab. It's about how researchers are bridging the gap, taking that detailed experimental data, and using it to build and, crucially, validate numerical models, computer simulations.
So moving from testing to predicting.
Precisely.
Yeah.
Because that's essential if you want to confidently design and manufacture these really complex, often weirdly shaped parts that absolutely have to perform.
Okay, let's unpack the problem side first. AM is amazing for complex shapes, saves material, but those stresses. Tell us more about this tensile residual stress. What's it actually doing inside the metal?
Well, think of it like the material is being slightly stretched as it cools, but the metal around it is holding it rigidly in place.
Okay, so it's trapped in a stretched state.
Kind of, yeah. And those internal pulling forces, they just want to pull the material apart eventually. They make it weaker, prone to warping, and they really hammer its fatigue life, its ability to withstand repeated loads.
And it's not just the stress, is it? The printing process itself can leave other little imperfections.
That's right. You often find defects like tiny voids, pores, maybe micro cracks hidden inside.
Little bubbles or gaps?
Essentially. But maybe even more interesting, particularly for this research, is something called anisotropy.
Anisotropy. Okay, break that down for us. It means the material isn't the same in all directions.
Exactly. Its properties, like its strength or stiffness, can be quite different depending on whether you measure along the direction the part was built upwards.
A build direction?
Or across the layers it was printed on.
Yeah.
The printing direction. Because it cools and solidifies layer by layer, the internal structure itself has a directionality baked in.
Which must affect how it responds to treatments later on.
Fundamentally.
Yeah. So the material starts with flaws. We need post-processing to fix it. People might use heat treatment, maybe shop peening, kind of like sandblasting with metal balls.
Those are common.
But they can have downsides like excess heat or just surface changes. Why is LSP the focus here? What makes it advanced?
Well, LSP tackles the stress deep inside the material, but critically, it does it without significant bulk heating, which can mess up the fine-tuned microstructure you got from AM.
Okay.
It's a surface treatment, yes, but it uses these incredibly high-power short laser pulses to force the material to deform plastically.
Plastic deformation, meaning it changes shape permanently on a tiny scale.
Right, and that deformation generates the good kind of stress, compressive stress near the surface.
This sounds less like manufacturing, more like science fiction. How does a laser pulse create enough force to reshape metal internally?
It's all about controlled plasma generation. It's a neat chain reaction. You need a few things. First, you coat the titanium surface with something called an ablative layer.
Like a sacrificial coating?
Exactly. Could be black paint, maybe metallic foil, PVC tape even, something to absorb the laser energy.
Got it, the absorber.
Then you cover that absorber with a clear liquid, usually just water, that acts as a confining layer.
Okay, water on top.
Now the high-power laser pulse shoots through the water and bam, hits the absorber layer.
Instant vaporization, I assume.
Instantly, the absorber turns into a superheated high-pressure plasma. But here's the key. It's trapped. The water layer acts like a lid, confining that rapidly expanding plasma.
So the water isn't just for cooling, it's actively focusing the pressure.
Precisely. It forces the plasma expansion to generate this incredibly intense pressure wave. We're talking units to tens of gigapascals.
Gigapascals. That's immense pressure, crushing force.
It is. And this pressure wave travels into the titanium as a shock wave. If that pressure is higher than the titanium's dynamic yield strength, its resistance to sudden force.
It forces that plastic deformation you mentioned.
Exactly. And that deformation is what introduces those beneficial compressive residual stresses deep into the surface layer.
So we're swapping out the bad pulling stress for the good squeezing stress, which should make the part tougher, more resistant to fatigue.
Correct. And importantly, because the laser interaction is so brief, nanoseconds long and confined, you get very little overall heating compared to something like heat treatment.
That's a huge advantage. But you said it's complex. It's not just point and shoot.
Definitely not. The results depend heavily on a whole bunch of parameters. The laser's energy, the spot size, the shape of the laser beam, how much you overlap the pulses, how many times you hit the same spot.
Lots of variables to juggle.
Which leads us right into the experiment these researchers conducted. They needed to systematically test these LSP parameters.
To figure out exactly how things like power density and beam shape affect the depth and amount of those good compressive strains in the TC4 titanium.
And they needed serious hardware. The team at ICMM UBRAS, they built a custom LSP system. It uses a solid-state ND.YAG laser. Puts out 10,064 nanometer light, can deliver up to 9 joules of energy in a tiny 10 nanosecond pulse. That lets them reach power densities up to a whopping 90 gigawatts per square centimeter.
90 GWCM alamidophoria. That's serious power density.
But these are often complex parts, right? Not just flat coupons. How do they apply it accurately?
Good point. They used a high-precision 6-axis robotic arm, a step SR50 manipulator.
Ah, a robot.
Yeah, for automated, really accurate processing.
Yeah.
It ensures the laser hits the surface exactly where needed at the right angle, which is crucial for treating parts that aren't flat.
Okay, so the laser treatment is done. Now the really tricky part, measuring that invisible stress locked inside the metal. How on earth do you do that accurately?
You need a reliable, standardized method. They use the hole drilling strain gauge method. It's under an ASTM standard, E837.
Hole drilling. Sounds simple, but I bet it isn't.
Well, the principle is clever. Think of the stress inside the material like potential energy. It's either stretched or compressed.
When you carefully drill a very small hole, you remove material that was holding that stress. The material right around the edge of the hole then relaxes, it springs back slightly.
You measure the relaxation.
Exactly. They use a tiny drill bit driven by a high-speed air turbine spinning up to 400,000 RPM.
400,000. Wow.
Yeah. Incredible speed for precise, clean drilling. They drill a hole maybe 1 to 2 millimeters wide, doing it in very small depth increments.
And they measure the relaxation at each step.
How? With a special strain gauge called a rosette. It has 3 tiny measurement grids arranged at 0, 45, and 90 degrees, glued to the surface right around where the hole will be drilled.
Okay.
As the hole gets deeper, the rosette precisely measures how much the surface strains or relaxes in those 3 directions.
So you get strain readings at different depths.
Right. And crucially, because LSP creates stress that changes with depth, they can't just assume it's uniform. They have to use a calculation method, the non-uniform stress field method, that accounts for that variation.
That sounds complicated. But it gives a true picture of the stress profile.
It does. And remember, if the strain gauge measures a positive relief strain when the hole is drilled,
that means the original stress was compressive. The good kind. Success.
Precisely.
Okay, experiment done. Holes drilled, strains measured meticulously. What did the results show? What did the titanium tell them?
Well, the first finding was striking, and it was about the material before LSP even touched it. It goes back to that anisotropy we talked about.
The directionality.
Yes. They found the initial residual strains in the samples cut along the build direction, the z-axis.
Okay, vertically upwards.
Were almost 10 times greater than the strains in samples cut along the printing direction, the x-axis, across the layers.
10 times. Yeah, just based on how the part was oriented during printing.
Yeah, nearly an order of magnitude difference in the inherent tensile stress. That's a huge deal. It shows how critical the initial AM setup is for the part's baseline state.
That really highlights the built-in flaw aspect. But did the LSP work? Did it convert those stresses?
It did, thankfully. After LSP, they consistently measured those beneficial compressive stresses, and they went quite deep.
How deep?
They observed the effect down to at least 1 millimeter below the surface. That's pretty significant penetration for LSP.
And where was the effect strongest?
The peak compressive effect, the maximum strain relief, was usually found a little below the surface, typically around zero point 0.2 to zero point 0.4 millimeters deep.
Interesting. Not right at the surface.
No, often the maximum effect is slightly subsurface.
The research also mentioned something about diminishing returns with laser power. You can't just keep cranking it up.
That's a key practical finding. Yes, increasing the laser power density generally increases the resulting compressive strain, but only up to a point.
Okay.
They found that once you go beyond about 10 to 15 gigawatts per square centimeter, the increase in beneficial strain becomes much less significant. The process efficiency really drops off.
So pouring more energy in beyond that point is basically wasteful.
Largely, yes, and potentially risks damaging the surface. So that 1015 GWCM5 seems like a sweet spot for TC4 titanium with this setup.
And did that anisotropy, the directionality, affect the LSP results too? Like, did the laser beam shape matter differently depending on the sample orientation?
It did. They tested different beam shapes, specifically a square versus a round spot. For the samples cut along the printing direction, x-axis, the square beam, a 1 by 1 millimeter square, actually produced a better result, deeper compressive stresses than a round beam.
Huh. Why would that be?
They suspect it relates back to the initial microstructure, the grain alignment from the printing process. The square shape might interact more effectively with that specific directional structure in the x-direction samples.
Fascinating. It really proves that the laser treatment has to be tuned, considering the material's specific history, right down to the build direction.
Absolutely. You can't ignore the starting point.
Okay, so we have all this complexity. Material direction, laser power, beam shape, overlap. Doing endless physical tests sounds incredibly time-consuming and expensive.
Exactly. Which brings us to the final, crucial part of this research, numerical modeling. Taking all this hard-won experimental data and using it to build a predictive computer model.
Moving from the lab bench to the computer screen.
Right. They fed all those measured strain profiles into simulation software.
What kind of software? Sounds specialized.
It is. They used ANSYS LS-DYNA, which is really good for simulating short, high-energy events like impacts or explosions or laser shock waves.
Okay.
And to make the simulation realistic, they needed to tell the software exactly how TC4 titanium behaves under these extreme conditions. For that, they used a specific material model called the Johnson-Cook constitutive relation.
So LS-DYNA does the physics simulation. Johnson-Cook tells it how TC4 specifically reacts to that physics.
You got it. It defines how the material strength changes with strain, strain rate, and temperature, all critical under LSP conditions.
And the big question, did the simulation match reality? Did the model accurately predict what they measured with the hole drilling?
It did, remarkably well. The comparison showed the numerical model could reproduce the experimental results, both qualitatively getting the trends right and quantitatively getting the numbers right, with an error margin under 10%.
Wow, less than 10% error. That's pretty accurate validation.
It's excellent validation. It means the model is trustworthy.
So what's the real-world value? Why build this accurate digital twin?
Because now you can use this validated model to predict the stress state in parts where you can't easily measure it physically.
Like what?
Think about really small parts, like tiny medical implants, or components thinner than the hole drilling method allows, say, less than a millimeter thick, or parts with really complex curves and features where you just can't apply a strain gauge properly.
So the model lets you see the internal stress in places measurement can't reach.
Exactly. You can simulate the LSP treatment on a complex CAD model and predict the resulting stress profile with high confidence. That's the engineering breakthrough.
Okay, let's wrap this up. We started with this inherent problem in metal AM, those bad tensile stresses.
Yep, the downside of that rapid heating and cooling.
But we found laser shock peening is a really effective tool to flip those into beneficial compressive stresses.
Improving fatigue life, likely closing up some internal porosity too, especially in critical materials like TC4 titanium.
And the big takeaway seems to be that how well LSP works is deeply connected to how the part was printed in the first place. That anisotropy, the build direction, it matters hugely.
You absolutely have to consider the material's initial state when designing the LSP process. It's not a one-size-fits-all treatment.
So it's this fascinating loop. Printing creates a flaw, LSP fixes the flaw, measurement confirms the fix, and modeling predicts the fix for future complex designs.
It really closes that loop, moving towards more predictable, reliable additive manufacturing.
So here's a final thought for you to consider. If these validated models can now accurately map stresses inside parts too small, too thin, or too complex to measure directly, think miniature medical devices, intricate cooling channels and turbine blades, how quickly could this predictive power change how we certify parts for safety?
Is this the beginning of truly digital certification, where we can computationally guarantee the integrity and durability of high-performance components before they're even physically tested? Something to think about until our next deep dive.